Hey guys, welcome back. Today's interesting topic is about multiplexer. So what's a multiplexer? Multiplexer is a logic circuit which has many input lines and a single output. So it can select one of the input based on the select lines. So as you can see, this is the circuit symbol of a multiplexer. So let us consider there are m input lines and n select lines. So the relation of how many input lines and how many select lines is as here. So it is m equals to 2 power n. So it is m equals to 2 power n. That means if you have two input lines, then we will have one select line. Similarly, if you have four input lines, then we have two select lines. So I think you can calculate the number of select lines based upon the input lines. So multiplexer, I'm gonna show you 2-in-1 multiplexer, how it looks. As you can see in this figure, this is a 2-in-1 multiplexer. So S is the select line, A and B are the inputs, where Y is the output. So based upon the S values, we are gonna get Y as output. If S equals to 0, then we are gonna get A as the output. If S equals to 1, then we are gonna get B as output. Okay, so as I can write over here, this is 0 and this is 1. So based upon the S value, we are gonna get the output at Y. So now we will write the Boolean expression for Y. So based upon the functionality, the Boolean expression at the output can be written as S bar. When S bar, then we will multiply with A. Then when it is S, we will multiply with B. So as you can see, when we want A, then S equals to 0. So substitute S equals to 0. Then it is 1 into A plus 0 into B. So this term is gone. What's remaining? A. Similarly, when we want B term, we will select S equals to 1. So substitute this S equals to 1 in this equation. That is 0 into A plus 1 into B. This term is gone. What is the output? B over here, A over here. So this is a basic 2-in-1 multiplexer. So we can have 4-in-2 multiplexer, 4-in-1 multiplexer. We can have different types of multiplexer. So all you need to do is to derive using this simple one, m equal to 2 power n. Okay, so if you have 4 input lines, then how many select lines you will have? 2 select lines. Okay, so now this multiplexer can be used as an universal gate. So how can we use this multiplexer as an universal gate? Till now we have studied NAND and NOR as an universal gate, but how can multiplexer can be used as universal gate? So let's see it. So now let's look at 2-in-1 multiplexer as an universal gate. So remember, there are 3 universal gates: NAND, NOR and MUX. Don't forget the MUX, which is important, and most of the people will ask this MUX. So as we know, the basic gate, NOT gate, which will give us output as a complement. Whatever we give, we'll get the complement. A we give complement A bar, 1 we give 0. So how can we design it using a multiplexer? So let us consider a 2-in-1 multiplexer. So as you know, we have one select line and 2 inputs. So it's so simple. So as you know, our output equation, our output equation is S dot A plus S into B. So this is our output equation if A and B are inputs and S is the select line. Okay, now we want a complement value. How can we get a complement value? So we need to get this complement. So whatever we are doing is select line we are getting as a complement. So what can we get? That S should be converted to S bar. We can use A as 1 and B as 0. What will happen? We'll get S bar dot S bar into 1 plus S into 0. So what is it? So it is S bar. Sorry for the disturbance. So this is S bar. S is converted to S bar when the inputs are 1 and 0. So what you need to do, substitute 1 and 0, then we'll get the S bar as a complement, and which will function as a NOT gate. So this is our NOT gate using 2-into-1 multiplexer. Now let us go for another gate, which is AND gate. So what is an AND gate? AND gate gives us output of A dot B. So how can we achieve this using a 2-to-1 multiplexer? As you know, this is a 2-to-1 multiplexer and its output equation. So one thing I can guarantee that, as you can see, this is an AND expression. So this is an AND expression. By this, you need to make this term to 0. Then we'll get as an AND operation. That's so simple. How to make this term as 0? How to make this term as 0? Give the input A as 0. Then we get an AND operation. So AND operation is already there in multiplexer. All you need to make is to make this first term as 0. How to make this first term as 0? Give input as 0. So this is how your 2-to-1 multiplexer looks. So we got an AND functionality using 2-to-1 multiplexer. S into B, S dot B, and the input A is 0. So now let's go for another gate, OR gate. This OR gate output is A plus B, but how can we get A plus B in this expression? How can we get A plus B in this expression? This OR gate is quite tricky if you don't know. This OR gate is quite tricky if you don't know distribution theorem. So what does a distribution theorem? So I will give you a small example. So if A plus A bar B is there, so what will be the output? So output is A plus B. If you understand this, then it's a simple one to solve into a 2-into-1 multiplexer. So A plus A bar B is A plus B. So how did this happen? So A plus A bar B equals to A plus B. So this can be brought by distribution theorem. What's the distribution theorem state? Distribution theorem states that A plus BC equals to A plus B into A plus C. So again, do this for, then we'll apply the distribution theorem for this A plus A bar B. Okay, apply this. So applying the distribution theorem, we'll get the value as A plus A bar into A plus B. As you know, this is 1. So 1 into anything is A plus B. So we got the value as A plus B. So if you understand this distribution theorem and A plus A bar B equals to A plus B, then it's super easy for you to do the 2-to-1 multiplexer OR gate. Okay, now let's go with 2-into-1 multiplexer gate. So we need to achieve this one in 2-into-1 multiplexer. How can we achieve this A plus A bar B in 2-into-1 multiplexer? Let's go back to the equation. So all we need to get is A bar B plus A. So A bar B is similar to like this, and we need to get something only 1. So as you think by now, I think you understood this input is 1. So S into 1 will get S plus S bar A. So S bar A is S plus A. We got our OR gate functionality. So let's look how it looks in this form. So this is our OR gate. So as you can see, S is a select line, A is the input, and B is input as 1. So now substitute these values in our output equation. So what we get is this output equation. Now, so we'll get this one, S plus S bar A. We know that A plus A bar B equals to what? A plus B. Now S plus S bar A. So S plus S bar A equals to what? S plus A. What is this? This is an OR gate functionality. Okay. Now let's go to another gate, NOR gate. So before getting the output of NOR gate, A plus B whole bar. So how this A plus B whole bar can be written? That's most important. Apply De Morgan's law. A bar plus A bar dot B bar. Now I think it's so simple for you to get A bar dot B bar. All you need to give this input as A bar and this input as 0. Then we will get our output as a NOR gate. So let's do it. So this is our NOR gate. What we get is S bar dot A bar. S bar dot A bar. But here A, we can get A bar from our NOT gate. If you can use 2-in-1 multiplexer NOT gate, then go use. We will not get a complement input. We will not get a complement input. This is an important point. So we will not get a complement input. Go get your another multiplexer and design an NOT gate for A bar. So S bar into A bar. This will be S plus A whole bar. This is an NOR gate. Okay, this is a NOR gate functionality. So now let's go for NAND gate. So this is our NAND gate and the output is A dot B whole bar. So A dot B whole bar can be reduced to A bar plus B bar from De Morgan's law. So have you forgotten what I said, that A plus A plus A bar equals to what? A plus B. Don't forget this. This is the distribution theorem. Now we are going to use this. So how can we get A bar plus B bar? So in using 2:1 multiplexer, let's go. So this is our NAND gate from multiplexer. So substitute this S and 1 and B. So input is not complement not available, then go get from multiplexer. So substitute these values in our output equation. What we get is, so we got the output as S bar dot 1 plus S dot B. So this can be written as S bar plus SB. Sorry, correction, it's B bar, okay? S bar plus S bar, S dot plus B bar. So now, as you know from distribution theorem, it is S bar plus B bar. Now from De Morgan's law, again go back, it is S dot B whole bar. So this is a NAND gate using a 2-in-1 multiplexer. So this is our XOR gate. All we need is this. From what? From this output equation. Substitute the correct values to get our required functions. Then we will substitute in the 2-in-1 multiplexer. This is how it looks for XOR gate. So this is our XOR gate in 2-in-1 multiplexer. So what is it? It's A into B. It's A bar into B at first, then after it's A into B bar. So what is this equation? This is an XOR equation, A XOR B. This is we got from 2-in-1 multiplexer. Similarly, we can do for XNOR. So this is an XNOR gate and this is what we need, AB plus A bar B. So how can we achieve this functionality from this output equation? Substitute the correct values in the inputs and outputs. I think you can do this after seeing this example. Even though if you want to answer, don't stop here, go forward for 5 seconds, you'll get the answer. So this is our XNOR gate. Okay, A into B, A bar into B bar, A into B, and this is our XNOR gate. I hope you like this 2-in-1 multiplexer as a universal gate. You can design any gate using 2:1 multiplexer, NAND gate and NOR gate. Never forget that multiplexer is an universal gate. You know, most of the people forget that multiplexer as a universal gate. So don't forget. So if you like this video, you can like, share or subscribe. If you do subscribe, that will help me a lot produce more videos, and I will try to improve my level to get the best information you want. Thanks for watching. Hope you like this video.